In the last video we looked at Pythagoras Theorem. We would use Pythagoras Theorem to find a missing length in a right angle triangle when we had two given sides. In this video we're going to move on and look at what we call the trigonometric or trig ratios. We have sine, cosine and tangent. We can use the trig ratios when we're trying to find missing lengths at angles in right angle triangles given certain information. Let's start off and look now at some triangles. What I'm going to do is label up each side relative to the angle x. If we take now this particular triangle, the longer side, that is the side always opposite the right angle, is called the hypotenuse. So this one is the hypotenuse. The side opposite to the angle, so looking directly at it, is going to be called the opposite. The one next to the angle is going to be called the adjacent. We have the hypotenuse, the opposite and the adjacent. So for this particular triangle, this is the hypotenuse. This one is opposite the angle, it's looking directly opposite, and the adjacent is the one next to it. If we look at this triangle, this is the hypotenuse, so this is the longer side. The opposite, which we called one of the two shorter sides when we were looking at Pythagoras, is just here. It's directly opposite that angle, and then the one adjacent is the one next to it. This one just here, we have the hypotenuse, we have the opposite, and we have the adjacent. This one just here, we have the hypotenuse, this one is the opposite, and this one is the adjacent. What we're going to do is look at the three trigonometric ratios. The first one is sine, and we can say in this particular case sine x. The sine of the angle is given now as the opposite over the hypotenuse. We can say that the cosine or cos of the angle, so cos x, will be equal to the adjacent over the hypotenuse. These are just ratios of the sides. The last one is tangent x, which we can write as tan x. Tan x is going to be the opposite over the adjacent. Later on in the video we will look at a mnemonic to remember these particular ratios. If we look on the calculator, we have sin or sine, cosine and tan, and later on we will use those two. So these are the three ratios that we can use to solve and find missing lengths and angles in right angle triangles given certain situations. Okay, so in this one it says for each triangle write sine theta, cos theta and tan theta as fractions. So if we look at this one now, we know, and just jotting these down, sine theta will be equal to the opposite over the hypotenuse. We've got cos theta. This is just now the ratio of the adjacent and the hypotenuse, and then we have tan theta, which is going to be the opposite over the adjacent. So if we look at this one first, this now is the opposite, this is the hypotenuse, so we can say that sine of the angle is going to be 3/5. If we look at this one, cos theta, the cosine of the angle, cos theta is going to be equal to 4/5. If we write tan theta, so tan theta is going to be the opposite over the adjacent, which is 3/4. So this is simply now introducing these as ratios. In all essence, if you don't take your work hugely far, these are not, they are important, but you're not really going to be asked questions just to write down what sine theta is. What we're going to do is use these facts to solve problems. So if we look at this one now, we want the sine of the angle. The sine of the angle is going to be equal to 5/13. That is the opposite over the hypotenuse. The adjacent over the hypotenuse is going to be 12/13. And the opposite over the adjacent is going to be 5/12. So that gives us our three ratios. When you come onto your work later on, you'll realise that tan theta is equal to sine theta divided by cos theta. So let's look at this one right here. Now we need to be a bit careful with this one as the triangle has been turned upside down. This is going to be the hypotenuse, this one is going to be the opposite, and this is going to be the adjacent. So we could say that sine theta is going to be the opposite over the hypotenuse, which is going to be 15 over the 17. If we look at cos theta, that's the adjacent over the hypotenuse, which is 8 over 17. If we look at tan theta, that is going to be the opposite over the adjacent, and that will be 15 over 8. When we're dealing with these triangles, whenever we've got sine or cosine, these fractions are always going to be less than 1. So if you got it the wrong way round, sine theta can't be 17 over 15, as the hypotenuse is always the longer side. So that's a brief intro. Let's look now at finding the missing lengths in right angle triangles given one side length and the angle. What we're going to do is use these triangles. You certainly don't need to, but it might help you out. So we're asked to find the length of the side marked x in each triangle. So this is finding a missing length in a right angle triangle given one side and the angle. If we were given two sides, we would use Pythagoras. But as we've not, we use the angle and one of the sides. Let's just look at this triangle. All I'm going to do is label up which sides we've got relative to the angle. This is the hypotenuse, this is the adjacent, and we're not interested because we don't have the opposite. We're trying to find the adjacent. What we can do here is use these triangles. When we first looked at the ratios, we can go ahead and use these, but often it's easier just to think of these triangles. If you want a mnemonic to remember them, some old hags can't always hide their old age. There's a range of different ones, but essentially it's SOHCAHTOA. So what we're going to look to do is find the adjacent. If I want to find the adjacent and I've got the hypotenuse, it must be this triangle here. So we're going to use this triangle to solve for the adjacent. What I'm going to do in that case is put now my finger over the adjacent. So we're just going to put that finger over here. And we do the cosine of the angle multiplied by the hypotenuse. So when we have the adjacent and the hypotenuse, we're going to go for cos. If we had the opposite and the hypotenuse, we would go for sine. If we had the opposite and the adjacent, we would go for tan. So what I can write now is the following. I can write that the cos, so cosine of 50 degrees multiplied by 8 will be equal to x. That's telling me this length. All I'm doing is multiplying cos of the angle by the hypotenuse. A nicer way to write this would be x is equal to 8 cos of 50 degrees. That's the way I'd write it, but I'm more than happy if you want to go ahead and write it like this. The first thing that we need to do is check that our calculator is in degrees mode. Little d here, if not, shift mode 3. That will put it in degrees. If you're doing this way, make sure you're closing off this bracket rather than having the cos of 50 times by 8, which is a cos of 400. I can simply type this in now as 8 cos of 50 degrees. If I do that, I'm going to end up with 5.14. So I'll write this as 5.14. That's going to be centimetres, and that now is to 3 significant figures. We would be given a level of accuracy, and I would suggest it was to 1 decimal place. Now, is that realistic? Well, it's certainly not longer than the hypotenuse, so we can say that that could be a possible solution. If it came up to be 9, for example, I know that that would be wrong. So all I've done is gone ahead and used now the second of these triangles. You will have to learn these triangles as they're rarely given on any exam paper. So let's look at this one right here. We've got the angle, we've got this side. Relative to that angle, that is the opposite, and this one is the longer side, so it's for hypotenuse. We can see that we're going to be using this triangle right here, and we want to find now the opposite. X is the opposite. So what I'm going to do is put my finger over the opposite, and I'm going to have now the sine of the angle multiplied by the hypotenuse. So I can say now that x will be equal to, and we can either write it in this form. I prefer to write it like so, so I'm going to say that's going to be 12 lots of now the sine of 80 degrees. So straight through a calculator with this, again, make sure you're in degrees mode. We're going to have 12 sine of 80 degrees. If we put that in, 11.8. So I write this now as 11.8. Again, we're not being given levels of accuracy. 11.8, that's going to be centimetres, and we can say that that is to 1 decimal place. So we can get a bit of practice with rounding to decimal places and significant figures. Is that realistic? Well, it's certainly less than the hypotenuse, and it looks fairly similar, so that's a fair estimation. So 12 sine of 80. A killer error here is to do the following. If we do sine of 80, and we could go this way, times by 12, that would be perfectly fine. The issue comes if we go ahead now, let's just go back in here and do this. This is what we don't want to do, as it will give us something completely different. So there we go. Make sure that you're writing it, and this is why I prefer to write it this way. Okay, let's look at the next one. So if we label this up, we've got now to find the opposite. So this is the opposite, this is the adjacent, so we're going to be using this particular triangle here. So we'll only ever have one triangle. We can see O and A appears in this one only, A and H in this one, and O and H in this one. So we're going to be looking at using the tan. I want the opposite, so I put my finger over that, and it's the tan of the angle multiplied by the adjacent. So we can say that x is going to be equal to 11, and then we're going to have tan of the 25 degrees. So straight through a calculator with that, let's do that, 11 tan of 25, and that will give us the answer. 5.129 and so on and so forth. So I'm going to say 5.1, that will be centimetres given to 1 decimal place. So I've rounded that to 5.1, but again, entirely up to you, or unless you're guided by the question. I generally go to one decimal place if we're using now integer values on the other sides. Okay, let's look at a slightly different example. What we've been doing each time is multiplying. So what I'm going to do is the following. We're going to look now at finding. So let's just grab up a couple of triangles. Let's just draw some triangles. We'll have one there, we'll have one there, and then we'll have one there. So what I've looked at in each case is finding an unknown side, and we've been multiplying. So let's say I've got now, in this particular case, I want to find this length right here. So I'm going to say that that is x. Here is my right angle. I'm going to say that this one is going to be, let's say this is going to be 5, and we will say that this right here is going to be an angle, and we'll say that that is 45 degrees. So if we look at this one now, if we label up the sides, this now is the hypotenuse, and this is the opposite. This time I want the hypotenuse. So what I need to do is go to this triangle. I've got now the opposite of my hypotenuse, so we're going to use this one. I want the hypotenuse, so I'm going to put my finger over the hypotenuse, and it's the opposite divided by the sine of the angle. This is a divide line. So what we can say then is the following. We can say now that x is going to be equal to the opposite divided by the sine of 45 degrees. So last time we were multiplying, we're now dividing. So if I put this in, 5 divided by the sine of 45 degrees, and that will tell us what the length is. As an exact value, it's 5 root 2. We can write that as 7.07, correct to 2 decimal places. So we can say from here, x is equal to, so x is equal to 7.07. that's going to be whatever the units are. Let's say we did this in centimetres, and that's given to 2 dp. So that time I was finding now the hypotenuse given the opposite. So if we just get rid of that one, let's now look at another one. So we can do a cosine one. Let's say we wanted to find this right here, and I said that this was going to be y, and we had now that this one was going to be 10, and this was an angle here of 30 degrees. So what I can do from here now is say, using the second triangle, we've got now this length right here. This length is going to be the hypotenuse. This one is going to be the adjacent. We want the hypotenuse, so I'm going to put my finger over the hypotenuse, and it's the adjacent divided by the cosine of the angle. So if we do that, what we're going to have is y is going to be equal to the adjacent divided by the cos of the angle, the cos of 30 degrees. So let's do that in the calculator. So we're going to have 10 over cosine of 30 degrees. There are some special angles. 30 degrees is one of them, and you'll see that later on in your work. 20 root 3 over 3, which is 11.5 to 1 decimal place. So 11.5, so y is equal to 11.5 units, and that is correct to 1 dp. We could do exactly the same here. If we wanted to go ahead and find the adjacent given the opposite, we would go ahead and use tan on that one. So there we go, that's nice and straightforward. So that is finding a missing length in a right angle triangle given one angle and one known side. If you've got two known sides, use Pythagoras. Okay, this time we need to find the angle. So it says find the angle theta, and then we've got these 6 triangles. Generally your angle will be theta or x. So if we look at this one right here, what we've got is the following. This is the angle, this is going to be the opposite, and this is going to be the hypotenuse. We know that it's going to be this triangle here. So what we can say now is that the sine, remember we're initially looking for the sine of the angle, is the opposite divided by the hypotenuse. This is a divide line. So we can say that sine theta is going to be equal to 8 over 10. We need to find theta. So what we write is that theta will be equal to the inverse sine. So this time when we're finding an angle given two lengths, we use the inverse. If you can imagine now, if we have x squared and we have the square root of x, these are inverse functions. Exactly the same. I'm taking the inverse. So on a calculator, again, always check that you're in degrees mode. This time to take the inverse, we do shift. So shift sine, and it will give us sine to the minus 1. So sine to the minus 1 of 8 over 10. I can close the brackets off if I want. On this particular calculator, you don't have to if you're lazy. That will give us 53.1. So theta is going to be equal to 53.1 degrees, and that is to 1 decimal place. So this time we're going back to the start and looking at this as a ratio. If we look at the next one, we have now relative to the angle, the opposite and the adjacent. We want to find the angle, so if we look here, the opposite and the adjacent is this one. We want the tan of the angle, so we're going to do the opposite over the adjacent. So I can say now that tan theta, so tan theta is equal to the opposite, which is going to be 6, over the adjacent, which is 2. Therefore, the angle theta will be equal to the inverse tan of 6 over 2, which of course gives us 3, and we can go ahead and find that. So on this one, we do shift tan. When you're looking for an angle, you need the inverse, and that is shift. So we have shift tan. Sometimes we call this arc tan, arc sine, or arc cos. Generally speaking, though, we will have tan to the minus 1. So 71.6. So theta is equal to 71.6 degrees, and that now is given to 1 decimal place. So 71.6. If we look at this one just here, we have the adjacent and we have the hypotenuse. We know that it's going to be this triangle. I first want to find the cosine of the angle, and we can say that that is the adjacent over the hypotenuse. So I can say that cos theta, or cos of whatever the angle was, whether it was x or theta, will be the adjacent, which is 5 over the hypotenuse. If you get this the wrong way round, you'll get an error. The ratio can never be greater than 1 in this triangle. So for example now, if I did shift cos and I got it the other way round and I did 20 divided by 5, what this is saying is find the angle of a triangle that has an adjacent of 20 and a hypotenuse of 5. The answer is it doesn't exist, as you can probably understand. So what we need to do is switch this over and do 5 over 20. It's probably an easier way of doing that, just starting again, and that is going to give us 75.5. So 75, so we can write now that theta will be equal to the inverse cosine, cos to the minus 1, of 5 over 20. If you like, you can simplify that to 1/4, and then we can say that theta, the angle right here, is given now as follows. 75.5, so 75.5 degrees, and that's to 1 decimal place. So if we just quickly whip through these ones, we've got now this is going to be now the opposite, this is the adjacent, so we would use tan, which is the third triangle. You don't have to use these triangles, you can just go back to the basic ratios that we looked at before, you can just use these. These ones right here, the ones that we introduced, you're more than welcome to just use those. The triangles are just a nice way of working with them. If we look at this one right here, we've got now the hypotenuse, so let's just go ahead and do that one. So we've got the hypotenuse, this is the hypotenuse, we have the adjacent, so we would use now the second triangle. This one right here, we've got the opposite and we've got the hypotenuse, so we would go ahead and use the first triangle. Okay, so that's the basics of it. If we're trying to find a missing angle in a right angle triangle, the information we need is 2 given sides and now this angle right here, which we look to find. Of course, if we were asked to find this length right here, we would simply use Pythagoras, and this one works out quite nicely because this is one of our triples that we saw in the last video. So we've got now 10, 8, this is going to be 6. Remember, 8 squared plus 6 squared is equal to 10 squared. This one right here, if we needed to find this length, we wouldn't need to use the trig ratios. This is simply going to be the square root of 6 squared plus 2 squared. This one just here, if we wanted this length right here, it would be the square root of 20 squared minus 5 squared, as we're looking for a shorter side. If that doesn't mean an awful lot to you, do check out the video on Pythagoras Theorem. Okay, let's move on. What we're now going to do is use our trig ratios, or the sine, cosine and tan ratios, to solve problems in context. So what we've looked at so far is just basic triangles. We're now going to look at, for example, in this case, tenths and 10 poles, etc., and look at solving the problem. So a guy rope is attached to a tent peg and the top of a tent pole, so that the angle between the peg and the bottom of the pole is 60 degrees. In part A, we need to find the height of the pole if the peg is 1 meter from the bottom of the pole. Okay, with these, it's just a case of drawing a triangle. Don't try and get all technical with this. Literally draw a triangle with the information that we need. So what we've got then is the following. We know that this is an angle of 60 degrees. Your triangle doesn't have to be, this is just a sketch. That is 60 degrees. The right angle is just here. So if we think the floor and the tent are going to be perpendicular. So we need to find the height. I'm going to call that h. This is going to be h. And we know the distance from the pole, so from here, the bottom of the pole to the peg, let's put that on, that's going to be 1 meter. So if we think about this now, all we've got to do is find this length right here. So if we label this up, we've got the angle, this is the adjacent, this is going to be the opposite, so we're going to go straight up to the triangle here. We want the opposite, so it's going to be the tan of the angle multiplied by the adjacent. So I'm going to say that h, the height, will be equal to 1 times by the tan of 60 degrees. So that's just going to be the tan of 60 degrees. As you get on with your work later on, you will see that this gives us a special angle and we get an exact result. I'll put it in anyway, but if we put this in, tan of 60 degrees, tan of 60 degrees is giving us root 3. So root 3, which is about 1.73, so 1.73. Is that realistic? 1.73 meters. It looks pretty good given our diagram. Okay, we need, it says on here, if the length of a rope is 1.4 meters, the length of the rope is 1.4 meters, find the height of the pole. So again, a new little triangle. We don't have to do anything crazy, just draw this up. So if we do that, so the length of the rope is 1.4 meters. So if we put this on right here, so length of the rope, that's what we've got from here. We've got now the angle is 60 degrees, and this time we're again looking for this length right here. So this is going to be the pole. So nice and straightforward, we're just going to get that. If we label this up, we have now the following. This is the hypotenuse, this is the opposite, so we need now to find the opposite. So I'm going to use this triangle, that's the only one where O and H appear, so I'm going to put my finger over O, and it's the hypotenuse multiplied by the sine of the angle. So we're going to have H, the height, is going to be the hypotenuse 1.4 multiplied by the sine of 60 degrees. So if we put this in a calculator, we've got 1.4 sine of 60 degrees. That's going to give me now 1.21. So 1.21, so let's put this in, let's write this in. We've got 1.21, that's going to be meters, and that's given to 2 decimal places. In part C, we need to find the distance of the peg from the base of the pole if the length of the guy rope is 2 meters. So again, quick sketch. So what we've got is the following. So we've got now the length of a rope, so just putting this on. So just checking the information, we've got now the guy rope here, and we're told now that that's going to be 2 meters. So let's just pop the information on. So 2 meters right here, that's 2. This angle is going to be 60 degrees, and we're looking now from the distance of the peg from the base. Well, that is what we're after. We're after this length right here, and I'm going to call that D. So that's a distance. If we consider what we've got the hypotenuse and we've got the adjacent. We need to find the adjacent, so I'm going to go ahead and use this particular triangle. So we can say that the adjacent, let's put this on, the adjacent will be equal to, and that's D, is going to be equal to the hypotenuse. Now, all I'm doing is using the hypotenuse multiplied by the cosine of the angle. So we're going to have 2 cos of 60 degrees. Cos of 60 degrees is another one of our special angles, and that will give us 1/2. So this is 2 lots now of 1/2, which is going to give us 1. So that will be 1 meter. You can check that on a calculator, but that will give us the correct answer. So as we can see, all we're doing is taking this picture and drawing some little triangles from it. Okay, let's look at this one. A ship sails 400 kilometers on a bearing of 0.75 degrees. How far east has the ship sailed? How far north has the ship sailed? So let's draw a little diagram up. With this one, what we're going to do is have our coordinate axis. So what we're going to do is have a bearing. Now a bearing is measured from north, it's measured clockwise, and it's given as 3 figures. So a bearing of 75 degrees will look something like that. So what we've got then is, if this one, in fact, it'll be a bit more. Let's something more like that. That's even more like that. That's probably better. So what we've got then is 75 degrees here. Therefore, this angle right here is going to be 15 degrees. Or, in fact, let's just put it in here rather than put that down. Let's just put 15 degrees, because we know that that will create a right angle. So this is 15 degrees. We've sailed 400 kilometers, so this is 400, and then all we need to do is go ahead and drop down the perpendicular. So I've got a little triangle here, and we can go and draw that, so it looks something like that. So we want to know how far east, so if we look right now, this is going to be east, that's the distance east, and I'll put that as E, and then the distance north is this one right here, and that's going to be N. So if we look here, if we want to find east, we're after the adjacent, and we've got the hypotenuse. So I want the adjacent, and we can say that the east direction is going to be the cosine of the angle multiplied by the hypotenuse, which is 400 cos of 15 degrees. If we look at the north, we're looking to find the opposite given the hypotenuse. So I want to find the opposite, and that will be the sine of the angle times by the hypotenuse. So this will be 400 sine of 15 degrees. Again, if you do some work later on, you will see when you come to certain problems, this will give you any point. So we would have this length multiplied by the cosine of the angle will give us how far we've travelled east and how far we've travelled north. So if we look at this now, we've got 400 and then we've got the cos of 15 degrees. We would expect this now to be significantly on here now, longer than how far it's travelled north. So let's just put that on. So that's going to be 386. So let's put that as 386. So 386 roughly. I'll let you round these accordingly. I really should. So 386.3. And then on the next one, we're looking how far north it's travelled. 400 sine of 15 degrees. So 103.5. So we'll say that's 104. So that's what we end up getting. You can, of course, check these out with Pythagoras as well to see if they stack up. Okay, a child is on a swing in a park. The highest position that she reaches is as shown. So we've got this picture right here. We need to find the height of the swing seat above the ground in this position. So let's just draw a little triangle. What I'm going to do is just sketch this up. So what we've got is something that looks like this. So we've got now, and this doesn't have to be accurate, it just gives us some idea. So we've got an angle just here. The angle is going to be 15 degrees. So we've got 15 degrees here. We've got 3 meters just here. And what I'm going to do is find the length of this right here. Once I've done that, what I can do is simply subtract that from 3.5, because I'm going to find this length right here. We know that all of this is going to be 3.5, so we can subtract that and that will give us the height. So let's just call this now the length. So if this is the length, what we have here now, relative to the angle, we have the adjacent. Relative to the angle, we have the hypotenuse. I want the adjacent, so I'm going to go ahead now and do the cosine of the angle multiplied by the hypotenuse. So we're going to have now on here, let's just change that over, we can say that L is going to be equal to 3, and then we're going to have cos of 15 degrees. So that's going to give me that, and if we do that in a calculator, let's work that out. So 3 cos of 15, we end up now with 2.89 and so on and so forth, which is going to be equal to 2.89 ... Therefore, and using my therefore symbol, the height is going to be equal to 3.5 minus the 2.89 ... and that will give us how far above the ground it is. So let's do that. 3.5 minus the answer, and we end up now with 0.60. So that's going to give us now 0.60, let's write this here, 0.60 meters, or if you like, 60 centimeters. Let's just check that. Yep, that's perfectly fine, 0.60 meters. Okay, so that's a nice kind of question in context, but once we've broken it down, it's fairly straightforward. Okay, let's have a look at another. A flagpole is fixed to a wall and supported by a rope as shown. We need to find the angle A, now between A, the rope and the wall, and B, the pole and the wall. So this is a pole, this is the rope. So if I just draw this up, I'll actually draw it on here. What we've got is a right angle triangle. So we can see it's a right angle triangle as we're given a right angle. So if we're looking at now the angle between the rope and the wall, the angle between the rope and the wall is going to be this one just here. So we're looking for that one. If we call this theta, we have now the opposite and we have the adjacent. So what we can say then is that theta, just consider now that this is the opposite, this is the adjacent. Using the triangle here, we can say now that tan theta, so tan theta is equal to the opposite, which is 2, over the adjacent, which is 5. So theta is equal to the inverse tan of 2/5, or if you like, 0.4. So let's go ahead and work that out. So from that, now let's do that. So what we'll have now is shift tan, the inverse tan of 2 divided by 5. And that gives us 21.8. So we can say theta is going to be equal to 21.8 degrees, and that is to 1 dp. Okay, so let's now do this. What I'll do is just store this, shift store A. So if you ever want to store something, shift store A in this calculator. So if you turn it back off, you can press recall A and it will bring it back up. Now let's think logically. What should this angle here be? Well, we know that this is 21.8. We've got a right angle, so this must now be 90 minus the 21.8, and so on and so forth. So what we can do is go ahead and simply subtract that. So if we do 90 minus A, so 90 minus A, that is going to give me 68.19, so 68.2 degrees, and that's to 1 dp. So that is giving me the angle between the pole and the wall, which is this one. Alternatively, if we hadn't spotted that, if we call this one x, we have now the opposite and the adjacent. So we could say now that the tan of the angle, tan x, will be equal to 5/2. Hopefully you will see the reciprocal of this fraction when we take the inverse will add up to 90 degrees. It obviously makes sense, but again, if you're new to the topic, you're not expected necessarily to spot that. So 5/2 is 2.5, and that will give us now 68.19 as we expected. So there we go. Now if they ask you to find the length between these points, it would just simply be Pythagoras. We could of course check our answer and use the trig ratios, but we certainly wouldn't need to. So if you're unsure if your answer is correct, if I just quickly draw this up, let's go ahead and do that. What we would, if I wanted this length right here, and we hadn't spotted for some reason that we could use Pythagoras, that's the right angle here. We might want this length, which I'm going to call, let's just call that L, and we've got that this one is 5. We found this angle, this was theta, and this was 21.8 ... We want the hypotenuse, given we've got the adjacent. So if I look now, I want the hypotenuse given the adjacent. So we can say that L will be equal to 5 over the cosine now of 21.8 ... that we have stored in the calculator. Now, if we just go ahead and do that, let's go ahead and do that. So remember, this is still stored in my calculator. So if I do now 5 divided by the cosine of that answer, we're going to end up with that length being 5.385, and so on and so forth. So if we write that in, that's 5.385 ... Let's just confirm that that is correct using Pythagoras. We know that a squared plus b squared is equal to c squared. So we can say now that L squared will be equal to 5 squared plus 2 squared. So we can say that L is going to be the square root of 25 plus 4, which is the root of 29, and we will see that it will give us exactly the same value. So the root of 29 gives us now the 5.385, as we certainly expected. Storing these in the calculator is always handy, especially if you're using more sort of involved questions, such that you don't forget. Okay, a marine runs 500 meters east and then 600 meters north. If he had run directly from his starting point to his final point, what bearing should he have run on? So let's go ahead and just sketch this up. So a nice bit of a wordy question. Let's do that. We've got now 500 meters east. So if we go 500 meters east, that's in that direction. Then what we've got is 600 meters north, which is in that direction. So what we could say now is that the hypotenuse of this right angle triangle is now going to give the direct distance that he would have run if he had gone straight. So we're looking at the bearing. So the bearing is going to be this angle right here. I'm going to call this one alpha, and I'm going to call this one beta. Hopefully you'll see that there's some relationship between this. So what we've got is 500 in this direction, there's our right angle, 600 in this direction. So what we could do is find this. Now if we wanted to find beta, we could look at this triangle and say, well, that's 600, that's 500, that's the opposite and that's the adjacent. So we could say that the tan of the angle beta is the opposite over the adjacent, and we could write that as 6 over 5 as they would cancel. If we think about this though, what we could have done is gone the other way and looked at the triangle in this particular way, and we'd have exactly the same. That is going to create now the rectangle that we're looking for. So this one would be 500, this would be 600. If we wanted to find alpha, we could say that the tan of alpha was going to be equal to the opposite, which is 500 over the adjacent. So that would give us now, and of course these two angles are going to add up to 90 degrees. So if we just do that, we can do the inverse tan of 5 divided by 6, 39.8. So that now is 39.8. So alpha on there is 39.8. So I'm going to write that the bearing, so the bearing is going to be equal to 040 degrees, and that's to the nearest degree. So nearest degree. Remember, your bearing is always going to be 3 figures. So that's that angle right here. You could have just found the other one and subtracted it now from 90. So if we do 90 minus, as we've seen, the inverse tan, let's do that, the inverse tan, 90 minus the inverse tan of 6/5, that is going to give us exactly the same value, because we're now looking at this angle right here, or if you like, the bearing. Okay, so that's quite a nice question, and we can set it up with a quick sketch. Okay, in the diagram, BD is equal to DE. We need to find the following. So BD is equal to DE. So let's find DE. So if I just draw this up, what we're going to have is the following. Let's just put this on. So we've got that, and we've got that. So this now, and I'll just label this up, this is going to be A, D, and E. So we're going to have A, we're going to have D. We've got a right angle just here, and we've got E. This is going to be 15, and this is going to be 12. Now, we're doing a video here on the trig ratios, but to find DE, I simply need to use Pythagoras Theorem. So we can say now from here that DE squared is going to be equal to, and we're going to have the following. Remember, we're trying to find a shorter length. This will be 15 squared, which is the hypotenuse, minus the other shorter side. So we end up now with 15 squared minus 12 squared. So DE will be equal to the square root of 225 minus 144. So if you want to go ahead and do that in the calculator or work it out manually, you certainly can. So we're going to have 225 minus now the 144, and that's going to give us 9. So we can say now that DE is going to give us 9. So DE is equal to 9 meters. You might have spotted that that is one of our Pythagorean triples. It's just the 3, 4, 5 triangle scaled up. Okay, we now want the angle DAE. The angle DAE, if A is in the middle, it is this one just here. So what we've got is this here. I'm going to use these two values. I found this one. Now that might not be correct. I certainly know that for this angle right here, I've got the 12 and the 15 that are given. If I look at that now, this is going to be relative to this angle, which I'm going to call theta. This is going to be the adjacent, and this is going to be the hypotenuse. So what we can say then is that the angle DAE, so DAE, will be equal to the inverse, and we're going to use the cosine. We've got the A and the H, so we can say now the inverse cosine, so shift cos to the minus 1 of 12 over 15. We don't need to break that fraction down, we can leave it as it is. So shift cos and then 12 fifteenths. 12 fifteenths, 36.86. I'm going to store that in if we need it later, and I'm going to say that's 36.9. So we can say now that angle DAE, So DA is equal to 36.9 degrees, and that is to 1 dp. So let's just check I've rounded that, and that will give us 36.9. So there we go, that's done. If we now look at this one right here, we need to find BC. Again, with this one, it's a simple case of using the information we're given and using Pythagoras. So we know that B to D is equal to D to E. So we've gone ahead and found that. So we can put this on right here, that this is going to be 9, this is going to be B, this is going to be C, and this is going to be D. We know that's 21. So all we're going to do is go ahead and find this length here. This is the hypotenuse. So we can say now that BC squared using Pythagoras will be equal to the sum of the squares of the two shorter sides. So we can say now that BC will be equal to the square root of 9 squared plus 21 squared. So let's just put that into the calculator and find that length. So we've got now the square root of 9 squared plus 21 squared as we're finding the hypotenuse, and that gives us 3 root 58. I'm going to leave it as 3 root 58 as that is an exact value, so let's put that in. BC is equal to 3 root 58. The reason I'm going to do that is that it makes my calculations easier if I've got to do anything else with it. Again, give it now to 2 decimal places, 3 significant figures if you wish. Let's just see what that would be. 22.84, which is not unreasonable given it's the hypotenuse, and we've got 21 here. Okay, we now want the angle BCD. So the angle BCD is going to be this one. I'm going to use the information that I've got. I'll just call that X. I've got now the opposite, and I've got the adjacent. So this is the opposite and this is the adjacent. So I can write now that the tan of the angle, because we're using this one, the tan of the angle, tan x, so tan x will be equal to 9 over 21. Again, we don't need to simplify that. And we just do shift tan now of 9 divided by 21, and that will give us the angle 23.2 degrees. So we can say that x is equal to 23.2 degrees, and that is to 1 dp. So there we go. All I've done is split this into triangles and used a combination of Pythagoras Theorem and our trig ratios. So hopefully that's given you a good introduction of how to find missing lengths and angles in right angle triangles. If you've got 2 known sides and you want to find the other, use Pythagoras. If you've got 1 known side and an angle, use trig ratios to find a missing length. If you have 2 known sides and you need to find an angle, use trig ratios.